supposed to be here with some handouts for you with the bios on it, but I don't want to waste a lot of time on that. Thank you for coming. Thank you to all our presenters. And we'll do it, I guess.
Just go right to it. Okay. Good thing I found a parking spot. Will you do the cane with the timing? Or is there a clock here? 15 minutes will fly. Anyways.
Do you want
I'll get a timer going. That's
Well,
okay.
just because we want to. It's like 15, right? Hard.
15-ish, I guess, just so everybody can get.
Yeah, exactly. So just.
Just go for it.
Yeah. Hi everyone. Justin Gray. Very nice to be with all of you. This is a very short and very quick, the fastest I'll hopefully be able to pull off, telling you about a project of my own that I've been working on for a couple of years, which will come out this year. Very, very quick backstory is that I'm obsessed with immersive audio. That's a sort of a simple way of putting it. Have been for a very long time. As an engineer, but actually specifically initially as a musician, as a composer, I come into my engineering area with a background as a bassist. So I'm the head of the production department at Humber College in the recording department, but at one point I was there only as a bassist, then a composer. And so this project is sort of bringing those two worlds together. When I first became sort of interested in the area of music in surround, outside of just being obsessed with film music as a listener, it really was to try and create. But fast forward, Dolby Atmos has exploded quite a lot over the last, more than a decade if we consider film, but then in the music world, probably about 6 or 7 years, and I have the pleasure of working in the format quite regularly, but always reimagining other people's music. And most of the time, not all the time, but most of the time that means the music was conceived of compositionally and recording-wise in a stereo capacity. Not even just a stereo capacity, stereo equals music at this point, right? We don't really talk about it, but just music equals stereo in most of our minds. But I've been thinking about it for a long time of just what music that I wanted to write and compose specifically for sort of 3 dimensions. That's the album cover. It's a piece of pendulum art that I made. So I'm going to fast forward through the idea of some of these things, but again, the project really starts with the intent of just composing music for sort of jazz world, Toronto, Canada extravaganza. Lots of our favorite colleagues are in this project. And just thinking about it from the ground up of what it means to spatialize orchestration, essentially. And so these are some longer slides for a time, but really what it comes down to and what the perspective of immersive audio that offers us is the opportunity to discuss perspective. Even in stereo or mono, realistically, any sort of music reproduction, we can talk about what perspective we want to give the listener. And the perspective, as a composer, that I wanted to give the listener is being inside of the ensemble, with everybody playing in towards them. But with 40 people doing it, and some of them being electric instruments, many of them being acoustic instruments, drum set, which ruins everything when we talk about acoustic string recording, and no offense to the drummers. Tabla, quiet instruments, kalimba, a lot of Indian instruments. I've studied Indian music for about 20 years. I actually lived there studying music very seriously for a long period of time. And instruments like sarod and sarangi are very, very quiet. So realistically, to have all these instruments situated around a listener to give the kind of proximity that I'm interested in, which is sometimes very close or sometimes more orchestral, is sort of an impossible seat to put a listener, even if we were to use scaffolding and try to record it in a native capacity. So that's the goal. It's to create a bit of a hyper-real scenario where the listener's in the middle of something. And of course, the Atmos format is one of the formats, but the most accessible that would be able to deliver that. Here's my studio. So, well, actually, it is important because when we talk about Dolby Atmos, we talk about how many speakers we're working with. I'm working with 11.1.6, but if we take out the 11 and think of 9 points on the main layer, 6 on the upper layer, and then 1 low frequency effects channel, what that really does is it does affect arrangements. Because if you know how many points that you've got for playback, and you make a decision as a composer or a producer to use a certain technology, whether it's stereo or 5.1 or Dolby Atmos, if I know that there's a limitation, I sort of leaned into that limitation and said, okay, well, my orchestrations will be associated with how many playback speakers there are. So a lot of times there are harmonies written specifically for 9 parts, or organizing certain behaviors in terms of counterpoint, spatial counterpoint, around the idea of the speaker limitation. That's not because it's better or worse, it's just because it is. And I made the decision that I would use this technology, so I sort of kept that in mind as a part of the orchestration process. So then what it really comes down to is getting to the studio. Now this was for a presentation at AES in New York about how to come into the studio prepared to do this kind of thing. I have a lot of diagrams, a lot of sketches coming in advance, knowing where I wanted every part. But the part that I think is the most fun is the opportunity to record things natively with immersive intent, which is not a new concept. This is a concept that we've had explored largely by the film mixers, film recordists, and also classical recordists for many years, decades at this point. Largely, usually, the idea of either, again, perspective, ensembles on stage, let's capture the room with enough microphones that when we can reproduce the audience sitting in the 10th row of the hall. Or let's do something like Morten Lindberg would do. Let's have the ensemble surround the microphones. So this here is an 11-channel microphone array. Let's have the ensemble surround the microphones and give the listener the experience of being in the middle of the orchestra. Again, an impossible seat, realistically. My thing was that this is an overdub style project. So this project was recorded over 35 days. This is Humber's studio, where I teach. So it's the Gordon Ragg studio. Many of you have probably been there. It's a gorgeous room. Although they would love to say it's a full-fledged studio, I think it's the perfect overdub room. Don't tell them I said that. The size of it, the reflections, the noise floor is super low. So every single day, every single instrument we set up, I sort of designed the microphone techniques around where that instrument was intended to sit in the arrangement. So this array was used for drums and string ensembles, where I'd move the strings around the ensemble. And the goal is, if I want the brass, let's say is a good example, to be behind me, not in the mix, in the composition. The mix is just a representation of the composition. Then I would situate them behind this array. Also have close mics, because I like close sounds. I like intimate sounds and more modern sort of capture. And then the purpose of the array is to capture the ambience of the space to get proper decorrelated sound, so that I don't have to use reverb after the fact to have that instrument feel like it's supposed to be behind me. And so this kind of array works really well for that. This is a 5-channel array of 3 Neumanns and 2 M150s for saxophones. And again, 67s and Coles and close capture up front, because I still want to hear the saxophones not sounding like it's an orchestral recording. But to have all of that decorrelated information for every single layer meant that, on top of the fact that the control room, let me see if I'll come back to a couple of these. I might not get there. The control room, we set up a 914 speaker system. So for the entire sort of duration, about 40 days of production in total in the studio, we're listening in real time in that way, and making decisions about exactly where the mics needed to be, and listening to an instrument saying, you know what, I need the reflections there in front of me so that the horns can live naturally behind. Or I actually do want kalimbas to be above me. How are we going to do that? Or I'd like a percussion ensemble to feel like it's, so let's get people up on ladders and play above the array and capture all the rest of the ambience. So it leads to Pro Tools tracks with about 1,000 tracks a song at 96. It's not fun. The computer almost behaved some of the time. And realistically, when we're tracking, we're not tracking into Atmos or anything. We're just tracking discrete channel, 1 channel to 1 speaker. And just building this thing one layer at a time, very much like film score recording, right? Where you come in, you already have a template, but it is improvised music, so the process as a producer was really to get the people to come in the right order. But we are spoiled for riches in Toronto and in Canada, and our players are so damn good that they know what to do and they come in and just kill it. I will say that, so we come to something like this is a bit more of a unique opportunity. These are Himalayan singing bowls, not your everyday instrument, a beautiful instrument. I'm sure someone has heard them before. It's my good friend Andrew Kay, who plays saxophone brilliantly, but also has collected about 40 of these in India. I've been there with him, one at a time with a tuner, making sure that they're as close to 440 as possible so you can play them like as a very functional instrument, melodically and sort of texturally. And so this array is seven microphones faced in, rather than out, which is our typical classical approach. It's an inverse array of microphones where 7 are on the lower level, Sheps MK4s, and 4 DPA 4006s on the upper level, all sort of equidistant to this spot right here. And what it does is it means that when you're sitting and you listen, I just take each of these, send them to one speaker each. Unlike the classical approach, which would have me, my perspective being the ensembles outside me, you're actually sitting where he is, except you're hearing it from outside, which is it's actually an impossible place for a listener to be, because the instrument is emanating this way, but you get to hear the attack from where he is. So one of the most beautiful parts of this process was when Andrew or any of the artists were done. Many artists don't really know that much about immersive audio still. They haven't heard it, or they certainly haven't had too much experience in the studio. But we all know that when you bring people into the control room, whatever format you're recording in, artists are very reactive. They hear something, they dig it, they don't like it, they want to replace it, they want to add more, they want to augment the groove, whatever it is. For them to be able to come, sit down, listen, and react in real time was very powerful. Because I saw learning curves where it would take about 30 seconds to explain what a 2-hour AES lecture would still fail to demonstrate. Because a musician who, means business listens and says, oh, I get it now. This is what this is. Okay, let me go back out there and play according to this experience. So this is a particularly fun introduction where Andrew sort of plays, and again, you're inside this thing. And this is just one of the many layers on the record. Let's see what other fun ones. Oh yeah, this was good. So reverb is fun, but halls are more fun. So for the whole record, I took all the soloists, because again, things are isolated. It was one of my rules for the record was I wanted it to be isolated parts. So I could do stuff like this. So this is one Meyer speaker at the Aga Khan Museum. I played back all the soloists into the hall and recorded the ambience with immersive arrays. So there's a 15-channel array on the main layer, a 5-channel array in the balcony, and a 4-channel array actually hanging from, there's the 5-channel, and a 4-channel array hanging from the rafters, which is about 120 feet off the ground. And just played the soloists back into the room to capture reverb, which is as old school as it gets, really, and just with more microphones. And so that represents the reverb for a lot of the folks on the record. So basically every single, here's some photos of just getting to, here's the studio. We don't actually, now we have an Atmos room at Humber, but at this time, it's not connected to our main studio. So we built it. We have 5.1 with the ATCs, and I brought a bunch of Genel X just to put it together and time aligned it the best I could, but it ended up sounding quite good. Let's see here. I think from a time standpoint, you get the picture. So at the end of the day, there's brass, there's strings, there's massive tabla songs where we've tracked one tabla in different pitches per speaker. A lot of it is acoustic recordings. Oh, there we go. That's always fun. But the intent now from a release standpoint is it was also all filmed. So for those who are adept with film, every day, 40 days of like 5-6 cameras on every person. So it's a full-length feature film. The release will take place at Massey Hall on June 7th in the TD Music Hall. So Doug's not here tonight, but we tested playing it back into their sort of 38-speaker immersive system. It's like taking Atmos and then playing it back into another object-based kind of panning system. It loses some of its intimacy and fidelity, but it gains some epicness, which is fun, and it's an opportunity to actually have more than 6 people all sitting like this, enjoy a musical evening. I have also, with Company 3, made a DCP, so I did a dedicated cinema master of the record, which is no small feat. You got to go, you got to prepare it properly. The way that I sort of wrote the master file is to essentially turn the ADM, which is the Atmos sort of format, into a multi-channel file so that when I got to the soundstage, we could actually still have a lot of control over various layers. because the objects essentially act like multi-tracks or stems at that point. And so there's a little bit of a tour going to LA and New York, Nashville, and London, playing the film back, sort of the album, the cinematic album film, what cinematic album I guess is the title, in those cities as an immersive album. And then from there, Blu-ray is the ideal because it contains video and Atmos at sort of high fidelity. And then we suffer through the streaming. But that is also the beauty, is the ability to get it to folks. And the very last one is that we have to have stereo. And as much as I would have loved the fold down to work for this, and I would have loved, and my wife and my kids and everyone else would have loved for that fold down to work, it just sucked. And so I remixed the record completely in stereo, just because we don't have control over how people listen to the music necessarily. So, yep, little labor of love. I'll certainly share it with the AES community when those opportunities come, and maybe later this year we might even be able to organize a little bit of one of the events with the community that can involve some listening. So that's 15 minutes. Thanks.
I'm light about the 15 minutes.
Okay.
Because I did leave a little bit of time for questions.
Perfect.
So are there any questions?
The Himalayan singing bowls.
Yeah.
When the gentleman is playing those things and he's listening to the mix afterwards.
Yeah.
What are his feelings?
Yeah, and I have a video of it actually, because we were videoing the whole time, so I've got some good doc content on this. So Andrew sort of sat down and he listened to it, and he had this feeling where he was immediately, swept away by the fidelity, but very quickly his brain realized, like, okay, at first it was like, okay, I'm playing the instrument, but very quickly he realized, like, wait a second, this is not what it sounds like to me. Yeah. It's sort of like what it feels like to play. I can reach out and touch the bowls coming at me, but the sound doesn't come to me that way. It's like playing double bass. When you're playing double bass, you never get to hear the sweetest part of it, which is in front, right? We get to hear we feel the vibration, we do a whole bunch of stuff, but the U47 or whatever that sits in front of the bridge, it gets the sweet spot. So it's a similar experience to that of coming back into the room. I mean, basically, whatever, trumpet, saxophone, going into the control room and saying, oh, well, that's how it sounds when you stand in front. That's actually pretty sweet. So he had a bit of a surreal experience that way, and I used that recording many times when artists would come in the morning. Yeah. I would just play that for them. It was nice and calm. It didn't sort of get anybody too excited, but really helped them to understand what we were trying to do, so that when I'm asking for some different types of overdubs, or like asking the vocalist Super Shankaran to do 12 layers, it made sense. Well, it made sense enough that they were willing to trust. But again, the ability for someone like Andrew to come into the control room and experience it in real time has a direct effect on what he plays next, which is really, at the end of the day, this is just about music. So who cares where the microphones are if the playing's not good?
But what he's listening to, what we're listening to, is completely backwards from what we would
totally
expect.
Backwards.
Yeah.
Which to me, I was like, that's what I wanted to. That was the vision for how I sort of wanted to achieve it that day. You could try it other ways, but the tricky thing about the Himalayan bowls, even though they feel loud in a room, they really don't have a lot of sound pressure. And when you start to get in and start to record them, it sounds really thin and really terrible unless you get right on the plane, and the proximity effect starts to sort of take place with the microphones. So yeah, it's a unique experience for sure.
Thank you.
Just one dummy head?
The one dummy head, it didn't make it on the record once.
Oh, okay.
It was always there. I gave everything its fair shot. Same with the Ambisonics. The Ambisonic mic that did make it in was a part of the reverb capture. We took a Soyuz to the reverb day with the Aga Khan Museum, and that one sounded fantastic. But here, when we were using full Neumann and Sheps and DPA arrays, the Neumann dummy head, for me as a mixer after the fact, I've like sitting there, it's awesome is I have close mics, medium mics, array mics, height mics. Usually you had 4 DPAs way up in the ceiling just almost at all times if the instrument was loud enough. As a mixer later on, you can really say, like, what do I want? Rather than reaching for a reverb or reaching for a plug-in or trying to use Haas effects to try to spread the sound around, it's just there. But yeah, just one, and I think it didn't make it in largely because it really does sound best in headphones. When we play it back over speakers, it loses some of its magic.
were saying there was almost 1,000 tracks of content. Were you mixing using the hybrid engine at that point, or?
I had to set up an RMU just for the record because it was at 96, and so it's HDX3 going, and then the Matrix 2 over the Thunderbolt card, which can handle 128 objects at 96. Was the first one that I could do actually because the Dante cards were impossible to find at that time, the Dante 2 cards. So then into a Mac Mini just for the renderer because it was just not working. During tracking, it's okay because it's HDX, but once you start instantiating plugins, and some of the immersive plugins are no fun. They don't really care about the computer at all. So when you try to use a bunch of them, now fortunately we had a lot of hardware in there, and we're as careful as possible in tracking. I didn't need to use a ton of plugins, but there are times when I wanted to like produce stuff and make it sort of surreal. So some of the sound particle stuff is super hungry. So I had to set up a separate computer, and I'm still using it as a result. It's like, it's sort of awesome.
Okay, I think,
Okay.
yeah, if you want to catch up with them later.
We'll do that. Thank you.
I want to keep things moving here.
Appreciate it.
Justin teased us a little bit with just, I don't want to let the cat out of the bag here, but we are in the formative stages of planning something for June, some sort of special event, and Justin may be part of it, so
Okay.
let's just leave it at that.
Well, thank you all. Appreciate it.
And I'd also, if you guys can give yourself a little bit of a bio, since I didn't do anything with that. Probably be just quicker if I let you do it.
Hi, everyone. I'm Greg O'Donnell. I flew in from Fredericton. I work post-production, and I'm in my graduating year of an electrical and computer engineering degree. I'm going to try to be respectful of the other speakers' time, so we'll get through this, but I was feeling a bit creative, so I decided to do a project with machine learning using speaker distortion, because long-haired guy, speaker distortion. So what did I do? Basically, I wanted to extract information about a speaker by making it distort with non-ideal near-field conditions. It's a fancy word for bad speaker. I wanted to get electrical damping and distance from the speaker. I mean, I'm working with what I have here, so the only thing I could really change in terms of the electrical properties of the speaker is chucking a series resistor on it, seeing if I can get information on that. So how is it possible using only audio? Basically, I trained the model recorded through a reference speaker microphone system. And why does it work? The idea is when a system artifacts, distorts, or has a nonlinear response, it is still giving you information. So we have a Tannoy bookshelf speaker. I removed the tweeter, tore apart the crossover so it wouldn't take any energy, and left the speaker port wide open. Open port created standing waves at 215 hertz, which I avoided by hitting it with a 90 hertz square wave. I did try 20, but it would have taken about 20 times the amount of time to record, because I would have had to window it over the period of 20 hertz instead of 90. I played the signal through a 1600 watt Class A H Yorkville amp. SPL meter measured it at 100 dBA. And the training library was recorded in the anechoic chamber at UNB. And then I snuck in at night and went to the student lounge and recorded non-anechoic data to test it. My setup, I really had to go with the SM57 on this one. I really couldn't run the risk of handling noise, and SM57 is really resistant to handling noise and has the off-axis rejection that I really wanted. It's mounted on a Dynamount X2R, which was programmed to basically do sweeps this way. Took about 6 minutes for it to travel across a 6.5-inch woofer while the square wave was playing the entire time. 3 sets of that was recorded at 5 different distances. The sets were recorded with no series resistance, 1.5 ohm and 3 ohm. I tried 8 ohm, but you could just look at it and tell, the damping's way different. So I tried to make it harder to visually choose. And basically the idea of the moving mic is there's a problem called overtraining in machine learning because it's a stochastic model. So if you record the same spot over and over and over again, the model will, because it's based off of variance, will kind of center towards it'll overemphasize parts of the distribution. So supervised and unsupervised machine learning are subsets in the field of AI, and then a subset of that is classifiers, which is what this is. Classifier it's basically puts things into a group. This is this group, this is this group, this is this group. Feature is going to be a term I'm going to use a lot. It could be a single data point, it could be a function of the data, it could be a single sample in a series of samples. A feature, in terms of AI, is sometimes interchanged with dimensions because you're literally, when you're visualizing it, that's kind of how you lay it out. I'm going to use the term principal component. This is the one kind of stats thing I kind of have to go over. So principal component, let's say this is sample 1, this is sample 2, this is all your data points. The idea of principal components is you can take that entire window of data, engineers would probably refer to this as eigenvalues, and you find orthogonal sets of those same things, and then you get rid of all the ones that don't describe the variance. So look at this one. If you got rid of E2 and described everything over E1, it wouldn't really, it would describe most of this data, but if you got rid of this, it would look like this wide. I'll move on, but that's kind of the low-level idea of it. So when I looked at the data on speaker loading, you could actually see it did separate quite well amongst the principal components. And it explained about 98% of the variance of the data. This is with a tiny resistor. You know, 1.5 ohm is nothing to like a 7 ohm speaker, so that's interesting. And then when I plotted distance, it was even cooler. You could actually see that it was fairly linear. So if we could find features that went along here, it could actually separate it quite well. So anechoic data, non-anechoic data, and this is damping and distance. So basically, the features of the actual audio, the signal itself is useless. It doesn't matter. Anybody who's worked in stats or anything like that, if you take a window and compare that, like of a periodic cycle, and compare it to the whole set, the cross correlation is going to be distorted. It's basically anybody who does DSP. It's like it would look like the convolution 2-rex. It would turn to a triangle. The data wouldn't distribute correctly. So we have to kind of make features that describe the data. So basically, we just do math, and then max of this is one feature. The average of them is the other. RMS is another. You name it. And I want more features, and then I want to get rid of them. Features can overlap. They can overemphasize sections of the data, cause overtraining, because maybe they're describing the same thing. So we need more features, then we need less features. So I used what I had. UNB has a very good biomedical engineering program. So I shoehorned one of their biomed libraries to come up with a bunch of features. Mean absolute value, zero crossing. I can go through all of them, but they have a bunch of them pre-done in an open source library, so I use that. Now we have too many features. So the plot on the left, this is an example of kind of the tricky part of this. The plot on the left has 85% accuracy on the anechoic data. When I ran it in the real world, 30%. Worse than guessing. The plot on the right is from adding 5 features that tested well by themselves, but you could actually see that the accuracy went down as I added features because they were covering the same thing. I used a technique called MRMR, which is a really good technique. You could also look at that PCA plot and see what direction the features go, and if they go in the same direction, get rid of one of them. That's the other way to do it, but this is like an automated way to do it. And then I ended up with only 3 features for the speaker loading, filtered down to 30 ranked features, And then basically every time a feature was added, I put in an algorithm that set a threshold for did it do better with validating the data. Did it do better? Was it more accurate? If it wasn't, it got rid of it. So results. This isn't showing up on the plot very well, but very good. LDA is actually a microcontroller friendly classifier that I used. You could actually program it with like a $2 microcontroller, but you could see it actually like draws lines that separate the data. I wish that you could see this in color. I have my laptop if anybody wants to see it after this is done. But it's a great candidate for regression. 75% accuracy for a single cycle, and you're running a 90 hertz square wave, you could just keep iterating over and over again to get a good estimate of the speaker resistance using only audio. Microphone distance was a bit trickier. Feature reduction had to be a bit, it wasn't as selective. You could see it kind of went all over the place. Rather than eliminating features at lower accuracy, I just basically made it so that it had to be over 10%. And that brought the features down to 4. And this is kind of the big result here. I got 90% accuracy with the non-anechoic data. When I was testing, all of the testing of the training data was only within subsections of the anechoic data. This is recorded entirely in different conditions, and I got 90% accuracy. Now, I could have admittedly gotten lucky, but that's really good. There's a 20% chance to guess this data for distance, and I had 5 different distance settings scaled basically by inverse square. So you can even see it caught this part, which is proximity effect from the closest capture. So in theory, if you use a periodic signal with regression, you could recall a microphone position if it's lost using only a super loud square wave. So I was very, very, very happy with that. And kind of the big takeaway from this experiment is distortion is still data. If I could do this from a chaotic environment with budget equipment, what if a chaotic sensor could be designed working backwards from feature space? Basically, consider it the other way around. With MEMS technology, the sensors are super cheap, and there's like no limits to geometry. The microphone arrays don't have to be symmetrical. Maybe we could have, beam-formed arrays that are not linear. You could have them comb filter and be a complete mess, and use them to generate metadata for ambient recordings and things like that. So I really hope nonlinear sensors kind of get further looked into, because I think they really would have a practical application in immersive audio, or higher order ambisonics and things like that. Another thing I just wanted to mention, because I brought up the biomed thing, I don't specialize in biomed. I just used the EMG library to analyze the waveform data. It was just a really good open source tool that kind of sped up the process. And I just wanted to credit the authors of that library. They're awesome. I took Dr. Chemet's pattern recognition class, which is what I used for most of this experiment. So most of the information I learned from that course. I wanted to thank Dr. Chris Rouse from the Wireless Power Transfer team for allowing me to use the anechoic chamber, Dr. Eric Chemet and the Live EMG team, Murray Ferris for his assistance, kind of learning to get with the times with Python. Engineering Endowment Fund, the Student Society helped me purchase the Dynamount X2R. I got assistance for travel reimbursement from the Student Society, and Bruce LeGros, a sound guy that I've worked with for many years, provided the shock mount and helped me with the anechoic recordings. So this project in no way endorses or condones specific commercial products, but I do kind of have to mention what I use. So, all right, are there any questions? Sorry if I kind of went a mile a minute there.
What do you envision in terms of commercial application for this technology? So, can I use this to recreate something that I'm trying to figure it out after the fact?
Yeah, so my idea of the biggest commercial application is, like, let's say Brent comes in the studio. Brent has the coffee. Brent's kicking out, he's wrapping my cables like this. You know what I mean? and he knocks over the mic stand, and you lose your microphone position. My hopes is that you should be able to recover the mic position by capturing the position using a square wave. That's kind of the immediate application. Now, I only got it in one axis, but I, in theory, could be able to do it above, I could do it X, Y, or, if I had the little cartridge assembly, do it off-axis stuff as well. So that's the main idea. The other one is being able to extract position data for surround and immersive applications.
Can you elaborate on that one a little bit more again? So this is after you've captured it using your analysis system for extrapolating that information. Is that sort of what you're suggesting?
Yeah. So let's say you have for audio, you want to have equidistant microphone placements for your arrays, for example. Perhaps if there was a microphone in the center that was not anything like that, that was out of phase, comb filtered, anything that at any point is different along the signal, I can envision a way for that to capture metadata to be interpreted from position. Basically, the idea is to somehow train the microphone so that it could move your virtual channels and things like that. Now, I haven't even begun to look into it, but that's kind of what I think would be a really cool thing to look into with that. So I don't know if it would pan out, but if it works one way, it should work the other.
I'd love to see this combined with your work. It'd be crazy.
Yeah, if you could set up all the microphones accurately while you're getting a coffee, that sounds. I mean, so to that point, you're suggesting the idea would be that in real time you're analyzing the data, and then from there you'd be able to extrapolate exactly where something should be based on differences.
Yeah, the way I have mine set up right now is that the signal doesn't matter.
Right.
The thing that the square wave is, the only thing the square wave is doing is giving that driver a really hard time.
Right.
And then the open port kind of has odd properties and near field conditions. I'm basically doing anything I can to make it just not be consistent at different mic positions.
Right.
And then I train off of that.
Okay, interesting.
Yeah, I can't actually use the audio, but I'm hoping a nonlinear sensor is already set up so that it doesn't behave the same along the surrounding it.
So you're saying that the non-linearities give you the coordinates that you need to recreate the original position? Is that essentially?
Yes. Yeah.
Oh, I think I get it.
I'm using.
Sounds good.
It's kind of just a stats-based guess based on how things went wrong at that particular position.
Would there be an eventual idea to have motorized mic stands or something that would take that data and move exactly to where it was before or something like that?
Oh yeah, that's actually what I used for the test.
Okay.
Yeah, I had to order the Dynamount.
But on a big scale, if they were permanent fixture microphones.
There would definitely be a challenge to practically doing it in a radial direction. I don't really know, but it's kind of a cool proof of concept anyway in one direction. Thank you everyone so much.
Kind of. Yeah, okay, that's close enough.
Can you work with it?
Sure.
Okay.
Anyways, my name's John Bailey. I've been stuck with the nickname Beetle since I was a little kid, just because when you grow up in a small town, that's how it is. Anyways, yeah, I've been working away in the recording industry since the sort of late 80s, I guess, and then working in various different recording studios and sort of making my way through the industry, and much like Justin, very much, mixing in 5.1 for many years, and then slowly morphing into Dolby Atmos and enjoying that a lot. And when the pandemic happened, myself and a bunch of other engineers, friends of mine, I found myself in a situation. I had just finished a major project, and we had to cancel the album release. It was too late to pull it from the distributor, so we were trying to figure out some sort of way of having some meaningful live performance on the internet. And of course, you know, when you go down that rabbit hole, you very quickly figure out that the internet is not gear driven, it's belt driven, and it's slippery. So essentially, the entire internet it doesn't have any kind of core synchronization. It's all built on best effort. Even with QoS, you're lucky if, you know, things are steady. And at that point, certainly all the streaming technology that was available from Source Elements or Audio Movers or all the various different providers are all based on either UDP, where you've got a fire hose of data sort of coming out of point A, and it's up to the recipient to try and catch it all. And if the internet is having a good day, then you can, and if not, you don't. And then, you know, WebSockets, various other sort of things, you know, that's, you know, things like Audio Movers use that. And then streaming technology, if you and I were both to start a movie on Netflix and we both hit play at the same time, mine might finish a minute earlier than yours does, right? It's just streaming it, and it's doing its best to sort of put all the packets in order, and nothing is synchronized in that way. Anyway, so you know, I would get on Skype with a bunch of engineer friends and complain about how everything sucks, and share all the sort of hilarious support emails I would get from various different software vendors, and had many conversations with, I don't think Anthony is here, but Anthony Kuzub is certainly somebody I was talking to a bunch, and Michael Noonan, various different people that are way smarter than I will ever be. And, you know, basically building an understanding of, you know, how to approach this problem. So we, you know, my friends in Los Angeles and one in Florida, one in Norway, all complaining about this stuff, and you know, the next thing the whiteboard comes out, and we kind of accidentally started a software company, and so here we are, 5 years in. So we've had a working POC of our system for about 2.5 years. So the idea is basically each of the participants connects to our back end, and we're doing a lot of pinging and round trip, you know, measuring packets and stuff, and building some intelligence about your connection to our back end. Everybody's internet route is going to be different, whether you're on land fiber or ocean fiber, or what kind of network you're on, how many hops you're going through. None of that should matter to the end user. It should just be, you connect, you do a thing. So basically, the first problem to solve is that if I'm going to push audio out to a group of musicians, the first problem that's going to happen, if I connect everybody on a low latency network, like a jack trip or something like that, the first problem is I cannot be absolutely sure when the audio is going to come out of the pipe. So the thing that's going to happen is very likely there's going to be a cacophony. Everybody's going to be hitting their strings at a different time. So we need to be absolutely deterministic about when the audio arrives at each person. So that's sort of the first part, and that's why we, as each participant sort of connects to a session, we do a bunch of intelligence about their connection, and, you know, basically resolving some of the clock issues in terms of NTP and everything else. So basically, now you've got everybody connected to our back end, and now when I hit the space bar and I push a bunch of audio through our system, I can be sure that everybody's hearing it at the same time, right? So, let me make this up a little bit. There we go. Sorry. This is very informal, but that's fine. Anyway, so basically what we do is our system, you know, we've iterated on this quite a bit over the years, but from our POC, essentially what happens is the front end of the application is much like many things. It's an Electron app built in React Native, and the back end is all sort of native C++ stuff. And it's essentially a headless DAW.
that runs underneath the application. So, you know, one of our mentors said to us very early on, this has to be so easy that my mom can do it. Meaning that if you're going to make a review session or any kind of session, there's a whole generation of musicians that have been left behind by, you know, we all know some musicians that have a setup at home. They've got Pro Tools or Logic, and they're able to record themselves and edit, consolidate the files, upload it to Dropbox, send you a link. That's like maybe 20% of the musicians. A lot of other people kind of get left behind by the technology, but they're brilliant. So the concept with our system is that you can join a session, you can have your coffee and toast in the morning, get in front of the computer. I run the transport, I do everything. You just have to be brilliant. So that's on the recording side. So essentially, when it's time to roll out the engineering effort on a project like this, you have to sort of go, okay, well, what can we do first? And then what can we do in terms of milestones, or what are we going to release in terms of the chunks of our platform? So basically, we started by doing the review and approval tool first. And the reason for that was that all of us were very much into Dolby Atmos. And once we realized that we could push, you know, like a dozen drum microphones, all sample accurate, through our system, we went, hey, wait a second, we can do Dolby Atmos with this. So we said to our devs, like, hey, can you just flip the driver on, you know, on the receive side so it just fans across the outputs? I said, sure, yeah, okay. And so we were like, okay, cool. And we just drop a bunch of transmit plugins on some pairs of object pairs or from a re-render, and then it's like, bang, okay, this works great. And our developer team was like, what are you talking about? That's crazy. Okay, so basically we decided to release the kind of review and approval tool first because it's a simpler UI, and it's a simpler sort of the staging the engineering effort of the different pieces that we add on. So basically what we did, so this is just a very simple drawing of like what happens when you're trying to push a bunch of audio downstream from point A to point B to point C to point D to point E. We have, you know, if you're just using WebSockets, you can sort of hit your space bar and have it show up at whoever the leader is on the session, let's say, and then push that again to a bunch of artists, and it's going to show up at different times to everybody, and then it's going to show up back at the producer again, all out of sync and everything else. And then you have some guests on the couch, you know. So this is a very sort of simplified, you know, we've changed a lot of things, but it's basically a time slot based system. So once we know we can be absolutely confident, we're going to set a point in the future that's like maybe 1,500 samples or 2,000 2,000 milliseconds or whatever. You can push the audio from point A to point B, have it show up at the leader. They're going to play piano, sing, do whatever they're doing. That shows up at the band time slot, and that's essentially where we connect everybody with a low latency bus. So they don't need to be sending multi-channel audio to each other. So if you have just a stereo kind of comms bus between all the musicians, it's sufficient enough for everybody to hear each other. And then each of them are generating audio and pushing that back to the producer. The producer's getting all of that, and every single segment of audio gets a unique timestamp. It gets a, you know, SSL 256-bit encryption and a unique ID, and that's all sort of pushed through our back end. So it's a sort of a pub sub type thing. I don't know. These are just some drawings I had laying around, but whatever. But essentially, you know, by provisioning a very high performance pub sub network in the back end, we're on AWS like everybody else. We can get down to about 150 milliseconds from the edge of your media server to the edge of the next media server. So with decent connections, you know, the system can be very powerful. The way that we have it working right now, we have a very sort of increasingly complex observability stack. So basically, we're able to sort of measure in samples the time of every packet, like every chunk of audio that moves through the system. So we can sort of measure the timing of those. And then in the application, maybe I have that time. I'm just trying to see if I have it here. Yeah, so we're doing a review and approval thing. This is, I can't really get it all on the screen, but it's just me looking bored. This is just a screenshot of the application, but essentially there's some indicators over here that we can show. If you're on the receive side, we can, the little RX indicator lights up in green, and we know that you're getting all of the audio and video. So every audio segment is tied right to the sample on the timeline from the host DAW, and every frame of video is tied to a sample. So the video is frame to sample accurate. Now, that also means that I always say it's like our superpower is also our Achilles heel, because if there's a problem with the audio clock, somebody connects with a pair of Bluetooth headphones and they use the microphone for video conferencing, it automatically drops down to 24 kilohertz. I don't know if anybody's done the deep dive on that, but it's very frustrating. So on the device side, we have to filter out Bluetooth microphones and prevent the AirPods or whatever they're using from connecting with 3 channels so that they stay at 48 kilohertz. And there's some SRC, if it's a 96K session or a 44.1 session, there's some SRC in the front end, but essentially that's how that works. So you can see over here, there's 4 little buttons here. So basically the green button at the top there means that the system's in screening mode, which means that there's a suite of plugins that runs in the host DAW. So the top one there is that's the main plugin. That gives us the pipeline between the host DAW, whether it's Pro Tools or Logic or Nuendo or whatever you're using. I've done sessions with DaVinci Resolve. We're working on a couple little quirks with Media Composer and Adobe Premiere and some others, but video NLEs can certainly host a session. But anyway, so the main plugin is the pipeline data between your host DAW and the SyncDNA standalone application. So it basically gives us transport. So much like if you're using Melodyne or SynchroArts or something like that, we get samples, timeline samples from the DAW. We get a bunch of other information, BPM and time code and things like that. So when you scrub the timeline on your DAW, it scrubs the timeline in SyncDNA. So that's what that does. It's an instrument plugin. I'll come back to why that is. And then the transmit plugin can be anything from even mono all the way up to 916. So, and you can have any number of transmit plugins, excuse me, in the session. So sometimes on a review session, you'll have some people that are on 2.0 on a laptop. You'll have somebody who's got a room that's in 7.1. You have another person who's got 7.14 or 9.16 or whatever. So you can set a bunch of live re-renders and just capture those on auxes and feed them to everybody as they go. And then the delay plugin, it only does anything when you're in screening mode. So it basically sits in your monitor path and it holds back the audio until you get, so you're hearing it at exactly the same time as everybody else on the session. So that's what it does. And then mix mode is that, except for your hands-on faders working, doing your normal thing, and everybody else in the session, all the guests, are hearing it at the next time slot, the one we call the studio couch. So I'll just quickly say, the reason that the main plugin is an instrument plugin is because when we release the next major decimal release, that's when we add remote record. And so when you have guests that join the session, their audio shows up there. So you can, with an instrument plugin, you can fan it out across any number of channels. So you can have a drummer that's got 12 outputs and a piano player that's got 5 or 6 microphones and somebody else. So it basically just fans across the channels, and you can have whatever EQ, reverbs, panning, whatever, and monitor them in real time with exactly the audio that you're going to get. So yeah, anyways, so that's, we basically push audio in either lossless in FLAC or in Ogg Vorbis. So if, this is just a stupid thing, this is one of the things in our job jar. When we get to it, the FLAC encoder only goes up to 8 channels right now, so we just need to set it up so that we can run 2 FLAC encoders side by side to do 16 channels in lossless, but otherwise we just use Ogg at 128K per channel. So yeah, but it's, the good thing is it's sample accurate audio across all of the channels. So when you're doing immersive, you will very quickly learn that you can't be having things that are not absolutely to the sample, because otherwise all the sort of timing delays and everything else become meaningless. So anyways.
You got time for a couple of questions?
Sure. Yes.
Does it have the capability to do spotting nodes? It seems like that would be really good.
Yes. Yeah, that's literally coming in. The guys are working on the back end pieces for that this week. So our marker UI is basically, we're working with the Avid scripting SDK. So basically, when you put a marker in SyncDNA, it makes a marker in Pro Tools, or well, certainly in this case with Avid, but it makes a marker in Pro Tools. And because it's a gRPC connection, you can basically move the marker in Pro Tools and it moves in SyncDNA. You move it in SyncDNA and it moves in Pro Tools. So basically the tracks where the markers show up and the back end for SyncDNA just need to be aligned in the profile, but that's it. But yes, that's literally next.
I was curious how that works from the perspective of the musicians that are playing and need some sort of monitoring. Like the people at the end of the pipeline, they're getting the whole sort of mix. But from the perspective of musicians that are, say, that second group past the lead,
Yes.
they're just getting the lead, they're not getting feedback from their.
Well, if you're on the stick, you know, basically you're not going to have any pre-recorded stuff. You're not going to have any click track or any reference tracks. So that's why in the fully expanded model of the system, you have a leader and a dedicated leader time slot. So that basically you can have a piano player with a vocal mic and they can be kind of like laying it down and have everybody else kind of following them. In the band time slot, everybody can hear each other. But in order to move, you know, the problem with streaming technology is that a lot of times, and you've probably found this, you can't even tap your foot to it, like it's doing this, right? So having rock solid audio that's like bit for bit identical to what it started out as, and moving that from this point to this point, you know, you've got computers on either end that have clocks that are at 3 or 4 gigahertz. It's the chaos of the internet in between them that's the problem, right? So.
But I mean, the band time slot itself is just a single thing. So
Yes.
for me to get the real time from another person that's basically parallel to me, I'll need that some of the time.
Are you talking like the people in the band time slot? Yeah, we connect them to each other with like a low latency network, like Jack Trip or Jamulus or whatever. Yeah.
So you're kind of able to say, like, jam these people.
Yeah. Yeah, I mean, within reason. I mean, you have to be sort of maybe a radius of maybe 150 kilometers, 200 kilometers max.
That's what I'm wondering.
Max.
Because I do this all the time.
Yeah.
They don't work.
Yeah, and it's very bandwidth intensive, you know. But it's also like
Jack Trip and it's close proximity. Right?
it's close. Yeah, like you'd have to be within. Best case scenario, you're all on the same POP, like you're all on Rogers or you're all on Bell. So you're not going out over the public internet. You're still inside Rogers POP, and then you're all geographically within a certain distance. You know, it is what it is. Like, you know, it's very limited.
John, look, I just did this from Italy,
Mm-hmm.
Los Angeles, back to Italy.
Yeah.
So the players are live in Los Angeles.
Right.
We're running it from here, like I said, and all they're doing is we're using jump desk.
Right.
We're just watching the desktop from LA come back and everything's in sync to us. Do you
Yeah.
know what I mean? Like, and that seems to work fine. Yeah, you know, like that's what we're doing. But we're not trying to do two people.
Exactly.
Like-
Yeah. Yeah. So this allows us to have X number of participants on a session. Obviously, if you're putting together, if you have a backing track that everybody's playing to, and you have people all in remote locations, they can't hear each other, not in any meaningful way. I mean, it would be a chaos. But you can certainly, we've done this it's sort of like, you do a pass and nobody can really hear each other because they're all in very remote locations. And then you can take everybody out of record and then just let them hear it, and then put the drummer back in record to let him sort of redo his thing against those guys, and then let this person redo theirs. So you can sort of it ends up like that in a recording studio anyways, right? So, you may as well sort of not spend 2 hours on the highway, So anyways, that's just a little sort of window into.
Sounds like something we might want to have a demonstration of in June,
Yeah, absolutely.
or maybe a whole session on
Sure.
audio over the wider network, right?
Hello, my name is Neil Parfit. I am a Toronto composer, mainly working on animation, but I've spent almost 20 years working as a score tech for other Canadian composers, working in Hollywood, here, all over the place. And one of the big issues is this refining workflows when dealing with preparing film scores for mixing and tracking, all those things. So I'm gonna just talk about how I was able to refine this over the last 2 years, and I did a major change recently that I've been testing that's literally saving 40 grand. So it's a pretty significant amount of money. With the techniques I've set up so far, worked on all this. So it's a proven sort of system so far. We've done 5 features, 220 episodes of animation, 100 plus episodes of an hour drama. So a lot of material has passed through the setup that I'm going to show you here. So most composers, when you're scoring, you're dealing with, usually there's 3. You got Logic, you got Digital Performer, you got Cubase. There's a whole bunch of other stuff like Ableton, Bitwig, all these things. But all those score assets, like all your individual elements, eventually have to make it to Pro Tools, love it or hate it. It's used on all the stages for tracking. It's used for mixing in 5.1 and up to Atmos. It's all the music editorial and final picture conforms are done in Pro Tools. And the final film re-record is done in Pro Tools. So all the stuff from any of these apps have to get there. And the problem with composing is you never have enough time. So this can't take a lot of time because we're always working to the 11th hour. Score assets are like click, dialogue, scoring demos for the chord stages, the stereo demo that the director, producers have approved, all your individual prelay elements that could be guitar, voice, all your synths, reinforced fake woodwinds, brass strings, percussion, choir. It all has to get there. So I'm gonna skip this for now. Doesn't matter. Logistics. If we're dealing with 45 minutes to 90 minutes of score, wrangling all that stuff takes a long time. And the longer that takes, the less time I have to write, the composer I'm working with has to write. So this just has to be a one-way process done once, because there's just so many moving parts. The setup has to work for all the cues. A cue is just a piece of music score. It has to jump between like a primary studio system, remote satellite studios. Your laptop has to go back and forth and just work seamlessly. So the idea was create a universal template that we could use on any film or show, set it up once, and we can deploy it for anything. So the idea is the template always has dialogue click, prelay elements, which are like synths, guitars, vocals, any of the individual elements, all the orchestral elements that are electronics. Those are all forced into stereo demos, and as well as we got prelay demos. It all gets pushed out to monitoring. And the idea is element A could be, for the course of the film, acoustic guitar number 1, or like a drone or a vocal. Like, it just stays the same the entire duration of the film or show. But how do we do this? Like, initially, we'd offline render everything. It would take forever. And offline rendering sounds good, but it screws up all the time. There's scripting errors, glitches. So the process we came up with was just do it in one shot, in one pass in Pro Tools. So Logic, 120 channels. Pro Tools is set up inline. It's always on. Even when it's not recording, it's just sitting in input monitor. And it's just on all the time. And it's Pro Tools HDX, so there's no latency, except for, I think it's 0.7 milliseconds, which is essentially 0. And Logic is smart enough where if you're using an interface that doesn't have those 128 channels, the first two channels are always stereo, so the session can work anywhere. And as soon as you bring back to the main system, all those channels are available again. So we can go back and forth from big systems to small systems to remote systems, wherever. So this is basically what it looks like. Logic is firing all that stuff into Pro Tools in real time. There's LTC timecode. So Pro Tools is always chasing. And that means when we record in our stuff, it's instantly in position where it has to be in the film or TV episode. So you never have to take those files and reline them up manually. It's already in position, and that's the session that they're going to get eventually. So you've saved yourself time. And because we're always monitoring through that, if it sounds right, it's done. Whereas before, you'd have to check each individual element, make sure it rendered, et cetera, et cetera. So at the end of the day, it kind of looks like this. Logic has its stuff. Pro Tools just has a doom scroll of audio tracks, taking in all the stuff. And it's just a one-shot process. Once it's all in there, we just import the Logic tempo map, so the bars and beats line up. Might break the cues apart, batch rename things, mute any tracks that are digital 0 or silence, and just check the clicks before we go to the orchestra's record stage. The time saved doing this, 3 to 5 full 12-hour days, down to the duration of the score, plus maybe 2 to 5 hours. So a significant amount of time saved. And then once we're done dumping everything in, that session just gets sent down the line. So if we're going to Abbey Road or Air, or if we're at Sony or whatever, we just give them that session. They can import it into their template and just keep working. So everything always just goes one direction instead of coming back. So here's how it was done for the first little while. From about 2013 to 2020, about 40 grand to do this. Logic's running an Army MADI card. 128 channels go out to Pro Tools HDX2, 2 MADI interfaces. We got our Sync HD to translate our LTC timecode. We got our clock, etc., etc. Fast forward to 2020, we're able to kind of put everything into an Avid matrix, which is a cleaner solution. Really expensive though, but way less gear. But then I started experimenting the past 2 or 3 months. A company called Audio Movers. They have this software called Omnibus, version 3. Basically, you can create virtual audio pipeline drivers. So I can create 128 I/O for Pro Tools. I can create one for Logic. I think you can have up to 4 or 5. And then you just matrix patch between the apps, and it digitally just pipes all that audio from one to the other. So now, everything is just done virtually. So 128 channels from Logic into Pro Tools, and it's $200 US. And so far with all my testing, it's been working amazingly. So $45,000 down to $200.
Wasn't that 45,000 Canadian?
I was gonna say 199 US is like 4,000 Canadian at this point. But the cool thing about this is because it was just a driver swap, the templates didn't need to be changed at all. You just basically tell Logic, hey, instead of using the 128 channel RME, use the virtual driver, and there's no reconfiguration. What we've made already just works. But I decided, you know what, because it is a virtual driver, it does induce latency, so that's an issue. And I like tracking real players on occasion versus all virtual computer stuff. So I decided to keep one HDX card. And because I had the HDX card, I could still use LTC timecode. And they're kind of working in tandem with the Pro Tools hybrid engine. So I deployed this. This is now the setup. $8 grand. It's mostly this. And I just retained this stuff from my previous investments. And Pro Tools and Logic are running on the same computer. There are some caveats and considerations. I can't monitor through Pro Tools in real time anymore because there is that added latency. But Omnibus lets you create presets and you can flip them with like a Stream Deck. So I have one where it says Logic to my outputs. And then when I'm ready to print into Pro Tools, I just choose the one where it's Logic to Pro Tools to my monitor. So that's easy. I'm still testing this. Because that driver is adding latency, I've noticed that when I dump in everything to Pro Tools, it is delayed by that exact latency amount. So the workaround so far is you just group select the whole thing and nudge back 128 samples if that's what your latency is. So that workaround is worth saving $45,000. If you're using it completely virtual, you're not using HDX, MIDI timecode over the IAC driver is a little bit more flaky than LTC timecode. So my workaround is just retaining my HDX and sync cards. The other con, actually, if your computer's at the brink when you're writing, this driver adds additional CPU overhead. So if you're at 98% on the brink of your computer exploding, this won't work because Pro Tools has no juice to do what it needs to do. The only consideration is computers are always getting faster, so hopefully that's faster than my audio needs if I update the computer. And for some people and some clients, this is more in-the-box mysterious, whereas hardware is very point-to-point. I know where my MADI cables are going. If I lose channels 1 to 64, chances are that cable got loose or something, the cat knocked it out. Whereas when it's in the box, it's kind of like voodoo. Consideration with that is you have to be very meticulous with software updates. Does everything work? Is everything compatible? Because anything could break it. So you don't rock the boat. If you're in the middle of a show or a movie, you don't do that update. You don't do that security patch. You just leave it until everything's finished and delivered. So that's where I'm at. I'm kind of excited to have dumped most of my Pro Tools hardware and switched to this really simple thing that I can run on my laptop now. So yeah, that's all I got. Any questions? Yeah.
You want to go? Okay, couple of things. You can run LTC directly out of Pro Tools with like a Dolby LTC generator.
Well, but keep in mind the Logic is controlling it, so it has to come from Logic.
I mean, you can use that plugin.
Well, yeah. So initially, like pre-2000 and whenever the Dolby production toolkit came out,
yeah.
I actually had these like 3-hour-long audio files of the LTC,
Right.
and I fired out a headphone output into the LTC input of a sync HD. But now I'm just using the Dolby LTC timecode generator and doing the same kind of thing.
Also, you could do a similar thing with Dante via and like a Dolby Bridge. Basically, you can basically use Dante via to route the same Dolby Bridge to multiple output channels, or even put it on a network and like send the whole bridge on a Dante network.
I should test that. I was testing the Audinate driver, and it was a little flaky.
That's the only thing with Omnibus will run over the network as well. You can run machine to machine straight up off the Omnibus.
Yeah. So I mean, so far I've just done it on one
No, but
computer.
like, I mean, that way you can run it. I don't know what the latency situation would be. I haven't looked, but you could run LTC to run it.
Yeah.
That's right, and just run it straight off your whatever existing network you have.
Yeah, and I mean, so far I'm just doing it old school, the matrix.
No, I mean,
Yeah.
That's something we because that's how we. At first, I thought we'd do it just to go, more, DAW to DAW.
Yeah.
Was the easiest way to do it over the same network, just with omnibus and no hardware whatsoever.
Yeah.
Awesome.
It's kind of liberating because I'm like, well, I can just bring this whole setup anywhere and do this while I'm on a plane.
And I have one more question. I'm slightly confused. So you're running it on the same machine, but you're running LTC external to the machine.
That only with a Sync HD. If it's all internal and I'm not using HDX at all, then it's all virtual.
Is there a way to get approval, sir?
Sorry, I'm just gonna add a tiny bit of caveat with the omnibus thing. That you need to have an AVB compatible Ethernet port.
Yeah, that's
If you're using it on multiple machines, right?
On multiple
Yeah,
machines,
yeah.
because otherwise it just doesn't show up.
See, I'm at the point now where like I hate maintaining computers, so I want it on one because you can't create multiple backups properly anymore. So I just want it all on one thing. Because if I'm maintaining mine, I'm maintaining a few other clients. So if they have 3 satellite machines, then there's 3 there, there's 3 here. I just would rather just die at this point.
But without a Sync HD, there's no way to get Pro Tools to lock tight to time.
Yeah, and I was testing that. Like
satellites.
MTC is flaky. Like I was getting like
Quarter frame, right?
I was getting like 3/4 frames out, and then it'd be 1, and then it'd be plus, and then it'd be minus.
Total
So
satellite's the same.
it's just that's why I've stuck with
Without
LTC because it's just bang on. So
Yeah.
yeah, there's always just niggly little things, but so far so good. I don't know. It's anyway, that's my weird composery workflow stuff. Yeah.
What kind of machine are you running right now?
Right now, I'm old school at this point. I have the 2019 Mac Pro, so it's 28 core. Sorry?
The Intel one?
Yeah, Intel 28 core. There's like 768 gigs of RAM on it.
Yeah.
It's still a beast.
Yeah.
But I'm waiting for like the next iteration of like the Mac Minis or
Yeah.
the
It's just not
M5.
big.
It's not quite there
Yeah,
yet.
I
Not
see.
enough RAM. So, but the eventual goal is to like not have these massive computers and just have something I can throw in my backpack and just work anywhere. And it's close. It's just not quite there yet. So, yeah. I guess that's it.
So my name is Buck, and I've been teaching audio for years at Trebas Institute and working on films for years. I started out doing live sound. And I did a major career change back in the 90s. It was live sound, and I working on soundtracks, doing boom, all sorts of sound work. And the basis of this is to solve 2 problems, which mostly independent filmmakers have, and that is dynamic range problems and dialogue clarity problems. Because I think if you mix around dialogue, which is the method I use to mix around, then everything else will fit nicely. But the problem is a lot of people don't understand the LUFs, the loudness units. So they're not really, like filmmakers themselves, they're not always getting audio people to work on it because they just can't afford it. So they're trying to do it themselves. So I fixed up a lot of independent film soundtracks for people. So I'm actually going to start with a quote here because I found this on Reddit and I thought it was hilarious. Where are we? Slideshow. And it's like, this is the problem I've been talking about for years, where we're at home and we're gain writing movies. Now, when you watch something in the IMAX, it's designed for IMAX, and they go through a lot of work to, have that big immersive sound, big dynamic range, but that's for IMAX. But what about most people streaming, watching at home, or especially independent filmmakers when they have a deliverable and it gets rejected? And I've worked with a lot of indie filmmakers for that reason, getting rejected from film festivals, getting rejected. One guy got rejected from a Prime, and he also got rejected from a cinema because he was going to do a cinema showing one night, a special screening. And he's like, well, how do I get there? I found your videos on YouTube. How do I get to the magic number of 7 on the Dolby processor in that particular cinema? And I said, well, send me some samples and let's work on it. So he couldn't afford to hire me to do the whole mix. And I said, well, that's fine. So we'll work something out where I'll give you the formula. So he sent me some samples, and I'm like, oh, well, here we go. So I'm using my Orban loudness meter. Was my main loudness meter until Sony Vegas, or Magix now, put a loudness meter in the program finally. So I had to use an external loudness meter to do tons of research to look at different levels. And his dialogue was at minus 45 on average. And his loudest peak was like minus 1 or 2. And I'm like, well, here's your problem, because the people at the cinema said, we can't play this. Same with a film festival years ago. They sent me the DCP reel, just the audio before it became the DCP. And I said, I don't need the picture, I just need the sound, because this thing's got to go, it's got to play. And the cinema itself said, we can't play this. And I've heard that a few times, we can't play it. I've sat in independent film festivals going, oh my God, is anybody on the same page here with sound? Because you can't hear someone's film, and then someone's film, and everything's too loud. So I'm just trying to come up with some sort of way that we can play, everything can play relatively evenly without taking people's creativity away, because filmmakers might say, you know, don't tell me how to do my art. I say, yeah, but your art is not just for you unless you're in a room watching your movie alone, which I don't think you want to do that. I think you want it for the masses. So there's got to be a better way. Now, let me rewind a bit with the loudness wars. I'm sure everybody's familiar with the loudness wars. Well, in cinema, it's the opposite. People want to get way more dynamic. It's like, yeah, but you can get dynamic with certain mixing techniques. So problem number one was dialogue clarity. So I got a tape recorder when I was 11 years old, and I basically never stopped. I just kept buying better gear. Eventually moved into Vegas Pro. I'm still using that for audio and for a lot of my film work. But the issue here was at a show I was mixing, and I didn't have many compressors or a lot of tools at this particular club because they're kind of cheap. So I was doing a lot of gain writing, and I had a little CD player beside me with all the 31 critical tones on it. And one night it felt like 20 people in a row got punched in the ear by one vocal blast. I'm like, what the heck was that? So it was around 400 hertz or something. And then I started to see a trend with this 200 to 400, 500, depending on the vocal, but basically the vowel sounds and the boxy area were the biggest part of the problem. And I thought, okay, so somebody said, well, you can put a compressor on that. I'm like, yeah, I could put a compressor on that, but can I do something before I put a compressor on? Because you might overcompress if you're using one tool. So my tools for soundtracks eventually, when I started working on people's soundtracks, was to do an EQ curve, which I call the D curve, and then do modest compression, and then finish it off with some mild volume automation to tweak it, basically for the, oh, that word isn't loud enough, or that sentence is too loud or something. So just kind of tweak it along with volume automation. But I started seeing this trend. Every show I was doing live, I would take pictures of everything, all my settings, right, before. Originally I had a piece of paper and I just marked them down, but when digital cameras, when you could see the screens, I started taking pictures, and I noticed, I keep doing this every show, why? And so a few thousand shows later, I'm like, well, no, actually, this is before the few thousand shows. It was a couple thousand shows. I was like, oh, I'm going to start doing this on soundtracks. Let's see if I can. Is it going to work? So I worked on this documentary that this producer is trying to sell to different TV stations around the world. And I said, well, I'm going to put this curve on the soundtrack and see if it actually works. And it does, because it's the same principle. The vowels, the boxy sounds are too loud. And I was always obsessed with getting the vocals to cut through the mix, because when I had a 4-track tape-based Fostex recorder, actually Tascam, a little pamphlet in it read how to fish out the vocals. So I've always been obsessed with fishing out the vocals. It's not like the vocals are too quiet, so turn them up. That's not the issue. It's about cutting through, because in most cinemas, when you go watch a film, you're listening to the sound through the screen. So there's an issue there with the perforations of the screen itself, the room reverberation, the bass response of digital cinema. So I started applying this to all the things I was working on, because it kind of cheats the dynamic range in it. And I'll play some samples after this because they're not playing back properly in the slideshow. But in order to, here, let's go here, measure these things, I wanted to cheat the dynamic range in that when the raw dialogue at minus 23.4 loudness units there, when it's on its own, that's how loud it is. When I do this decurve thing, I lose about 1.5 decibels. Then, when I compress it, I lose another 1.5 decibels, plus or minus. And then when I do volume, compensation, or gain makeup, I end up getting back to pretty much the same level, but it sounds different. So if the dialogue is cutting through, and it is technically the same loudness as the raw dialogue, but it sounds like it's cutting through more, we don't need to have big sonic blasts, unless you're a big Hollywood filmmaker and you're going to do what you want. But for most people, the indies for sure, they're not really doing that. So they're ending up with these soundtracks that are a lot of times unplayable, as I mentioned. So let's see if it does play, actually. I'll just give it a shot. Otherwise, I'm going to play the videos at the end so you can actually hear the results. No, so let's move on. Oops, you see, it keeps doing that. Sorry, I lost the mouse. I thought this technology was supposed to help us. What's it doing here? Come on. Ah, here we go. Moving on. So I decided one day I was going to map it out because I had a class of students that were like, well, where do we start? I was trying to find answers online for years, and I'd get a lot of different message boards from people saying, I do this, I do this, I do this, and I said, but we're all doing slightly different things. Is anyone going to be doing about the same thing to have, I'm not saying an absolute standard, but more kind of that everybody's going to play back so you don't have to ride the remote, or you go to the theater and all the films play back, plus or minus in the right range of being comfortable and being able to hear the dialogue, instead of killing people with a loud blast of sound or something. The people are obsessed with that sometimes. So that's comparing what we're actually hearing in the cinema, in the real world, compared to the digital world. Because if you keep your soundtrack under 30 dB dynamic range in the negative numbers, so like -2, I like -2 as the true peak, down to -29, but I prefer -27, you'll still get the room making a lot of the sound, especially with the modern digital sound systems. It's going to be louder than it is on the soundtrack. So the misconception for some people who I've talked to is that, well, that's only that dynamic. Yeah, but now it comes through the speakers into the room and you're getting more dynamics, right? And I've measured this. I'm the nerd that sits in the movie theater with an SPL meter and a notepad. My friends or my wife are like, what are you doing now? She understands, but my friends don't understand. There's a way to cheat loudness with sound mapping and cheating it a little bit with, and I've studied films. I get the soundtracks and put them on my timeline and I study them. If you get rid of the sounds, like make them almost nothing right before the jump scare and do this thing called the punch and shelf. I didn't know what else to call it, so I call it a punch and shelf. It appears that a ½ second punch with a 3 to 4 dB shelf as it sustains is way more effective than that just punching up to -2 and sustaining for that whole, for that whole time. And it is a noticeable difference. And so I've done lots of experiments with students saying, I'm not going to tell you what's what. I'm just going to play A, B, C, and D. And then you tell me which one you like the best. And 80% of the time, people choose ½ a second. Some people go, oh, I like the whole second. But then it's noticeable. And some people like, I'm only starting with ½ a second, and then 1 second, and 2 seconds, and 4 seconds. And 4 seconds is just doesn't seem to work for most people. So I ended up getting a lot of comments on my YouTube channels, which I like, and I leave the negative ones up there because I'm not going to erase anything, because that helps me too to read negative comments. And a student mentioned this to me. Have you seen the new Dune film? I said, no, I haven't. So I downloaded a copy, and I'm like, oh, okay. So she told me about the helicopter, big, whatever they are, what are they, dragonfly helicopters or something. And they come roaring in. I'm like, oh God, yeah, that's actually quite noticeably loud. And so I love the positive comments because it makes me want to work more. But then I get the negative comments, and you gotta deal with them. Why is everyone talking in listening volume instead of digital level? And I have answers for all these, right? I answer as many questions as I can. But it's like, well, because that's what we're left with at the end. That's what the audience is hearing. The audience isn't hearing the digital stuff. They're hearing the analog stuff or the SPL on the open air. So we're kind of making it for them. There is so much more to this. Don't think after watching this video you know everything. You need to do a lot of research. I know. It's an evolving thing. I haven't got all the answers. I'm doing my best to come up with, you know, a solution, at least for people who want to try the solution. I even tell some people, you don't want to try it? Don't try it. I don't care, right? But if you're having issues, at least try it. If it works, you might stick with it. If you find a different way, you find a different way. But I found that this works. Saying that conversation has to be 50 to 63 dB, I didn't say that. I said 50 to 63 on the video, and I had to point the timestamp to say that's what I actually said. So, and that's, oops, this seems to still work. That's where the comment comes in. Then I thought, what if I just see what the streaming services are saying? And I went to Netflix, being Netflix, one of the biggest, and lo and behold, under the best practices, it's like right there, -27, plus or minus 2. So I already thought -27 was kind of the sweet spot for dynamics, for dialogue, with your true peak at -2. And I think they even suggest a true peak of -2.3 on one of the best practice pages too. But there's, for anybody wanting to deliver to Netflix, there's a ton of information depending on if it's Atmos 5.1, you know, stereo, etc. And that's what they say. And I found this to be interesting from the standard. And in 2017, when I was presenting to AES members meeting, I didn't realize that Gil was in the audience who came up with this. And now I know you're in the audience. So. But, and that was a very good conversation because you just came up and quietly said that you came up with it. And that's amazing. So I do need to contact you at some point to further this research. But Netflix, they both say about the same thing. Listeners desire subjective loudness of audio programs to be uniform for different sources and types. We don't want to tell you how to mix your movie. However, so, you know, and I found similar results from like HBO Max, and there's, you know, all the different music streaming services, which is a different topic. But I was sitting in the theater. Let me take a look at the time here. I'm going to be done in a minute here and just play one thing. That's just a close-up of what I found doing spotting notes for The Dark Knight as a movie, and lots of movies since then. But that's what I do. I just take a sheet, I take a notebook, and I transfer it to a sheet and assess it at the end and map it out to see like the dynamic fluctuations. And then now sometimes I take the waveforms as well. So I did want to play quickly, if I can find it here. Oh, here, just 2 examples with the D curve and no D curve. Media player, play, okay.
I was greatly impressed with the device, but questioned its show value. Warner Brothers, their efforts tolerated then, but envied now. I was greatly impressed with the device, but questioned its show value. Warner Brothers, their efforts tolerated then, but envied now. I was greatly impressed with the device, but questioned its show value. Warner Brothers, their efforts tolerated then, but envied now. I was greatly impressed with the device, but questioned its show value. Warner Brothers, their efforts tolerated then, but envied now.
Here's the A-B comparison.
I was greatly impressed with the device, but questioned its show value. I was greatly impressed with the device, but questioned its show value.
So it's subtle for some people and noticeable for other people, but it's not an extreme thing. It's just a little sweetening. One more quick little video and then I'll be done. I don't want to play the digital cinema package that was screwed up because that would blow the speakers. So I'll play, oops, what happened there? I'm not going to mail this. Open with movie player.
One day, I saw a child playing with a ruby the size of a tangerine. Bandit had been throwing them away. With respect, Master Wayne, perhaps this is a man you don't fully understand either.
Here's the action scene from the same film.
Now in the IMAX, add a lot more to that. And the dialogue you can hear because everything is quiet, much like this room. This is a great sounding room for music. But it's kind of like that. You can hear everything in the IMAX, but at home you can't. That is a problem for bringing things home or streaming versus like independent filmmakers trying to figure out their soundtrack. That's all I got. I realize it's 8:45, so I don't want to take up your time. Unless there's any quick questions.
John, you're up.
It's in my hand. Do you want that clicker?
Yes, please.
Bottom. This one.
Which one?
That one's forward.
Thank you. Okay.
What one? And lasers.
Oh, yeah.
Lasers at the very top.
Thank you.
I hope you paid attention, John, because you have to teach me how to use things.
Careful, all the corners. Well, there should be good.
Oh, okay. All right. Let me just see how this goes. Oh. Let's look at an impulse response and just a little education just to show you what it is. If you have put a sharp pulse into a system, then it's going to give an acoustic delay and then give a response like that through the system. If you put a music signal in, it's going to take every sample of that music signal and draw one of those things there. So this sample here will draw that. And you add them all up and you get the music signal, right? So what's happened between the input to the system and the output to the system is the spectrum has gone through what the impulse response has. The sharp pulse was dead flat. The impulse response has got this frequency response of that system in it. And so the ratio of these two spectra here will also be the impulse response equivalent of the system. So the impulse response tells you everything there is to know about a system between that loudspeaker and that microphone. That's the whole point, okay? So, and we usually measure it with a logarithmic sweep. And it's a good way to do it. There are other ways. You can use real music if you like. You've got to make sure that the music has got all frequencies in it, so it's spectrally dense, but it'll work that way too. Here's a measured impulse response, and we'll talk about it later. You'll see this one again later. It's got a single reflection in it. And when you look at it closely, this is blown up here, okay? And if you truncate at this point here and remove that reflection like this, then the spectrum changes from the green one, which is all the data, that's the whole thing, and just the red thing, you see? So the high frequencies are pretty well done, actually, because you've removed this reflection. So the high frequencies pretty well finished speaking in the first millisecond or two. And so you're doing pretty well. But the low end is all screwed up because the loudspeaker is still ringing even down here somewhere. So you can't do that, right? It's screwed up the low frequencies, and we'll get back to that later. Here, this is what we do when we truncate the impulse response. Okay, this for example, is a second order system set at 70 hertz, high pass, second order Butterworth. It's typical small bookshelf speaker, that sort of thing. And if you truncate it here, then you get the red curve. This is the original, okay, there's the original loudspeaker, and you get the red curve. And you get less than 0.2 dB ripple down to about 200 hertz. So the point is, if you measure that impulse response and then lop off the room reflection, you'll be okay above 200-300 hertz. The response will be fine. And I think we all know that, right? And you can see it here in this red curve here. That's probably the original there is this one, right? Okay, the red curve is not bad. You're getting some loss. But anything else you do, suppose you take a cosine, just a simple cosine, or a raised cosine, it cuts off more of the impulse response. So it's probably not as good as just truncating it. So we can argue about that till the cows come home, but it's okay. This is my living room. There's a KEF 102 being measured at a meter. Sits in the middle of the room to make sure it's equidistant between all these things, right? And there's the impulse response. It's a mess. There's room reflections everywhere, right? I could never figure out exactly what that was, but I think it's one of the mirrors at one end of the of the room. Anyway, so that's what happens when you do that. And this is what we also do. We measure it near field. Don Keel published one of the first papers on this 51 years ago. And if you take that impulse response, then you can see it here. It's very, oops, how do I go backwards? Well, probably this way, right? Okay, so, whoops. Oh dear. What's happened is I have a nosebleed. Oh dear. Well, we'll just have to keep on going. Sorry about that.
Canadian winters.
Yeah, that's right. Yeah. Okay, I'll try to keep going, and we'll see how things go. So, let's see. I think we. Yeah, move on here. So, if these results here are the calculated diffraction for that cabinet, okay, and here is the measured near field and far field responses with the truncated impulse response. So the one way that I measure a loudspeaker is I take that impulse response, and we can look at the two of them. We have the near field and the far field, and we have these two things. And so if we apply the diffraction correction to the near field, we can make it like the far field and put the two together. And when we do that, we get a complete response like this. So this is sort of anechoic, because the near field response was so close to the speaker that the room reflection didn't matter, right? That's the whole point. Okay, so that's the diffraction way of doing things, and I did that last year in a paper. This is an example of a simple model which I'm working on. I don't want to talk more about that. That's going to be done later on. Okay, suppose we want to measure a speaker, but there's a strong reflection, like that driveway there. Okay, how do we do this? Well, we could do it in the following way. Or let's first look at what happens with loudspeakers. If we mount a loudspeaker and rotate it around the center of the cabinet, then when we measure it on axis, you get the top curve. When we measure it at the back, you get the bottom curve. If, however, you mount the loudspeaker so that it's mounted at what I call the acoustic center, then what happens is all the responses fall on top of each other up to about 500 hertz. So this acoustic center is a real thing, and it shows you that the loudspeaker at the low frequencies acts like a point source that's in front of the driver by about half the cabinet width. And that's quite neat to know, and that's going to be useful as we work out one more way of measuring the loudspeaker. So this is a boundary element calculation showing you what happens with the cabinet when you do that. It's quite incredible, really, because even back here, you can see that the velocity is already pointing back to that acoustic center, which is about there, I guess. You can see that, right? It's sort of interesting to notice that. Anyway, we'll generate a computer signal. We'll look at that. We'll capture a reference of it and the microphone output. We can have the spectrum of that sweep signal is a pink noise-like. It goes down as 1 over f for power. 1 over f squared for power, I guess. 1 over f for amplitude. Wait a minute. 1 over f for power. And there's the other spectrum. The ratio of those two is the transfer function. And from that, we can get the impulse response, right? As usual. So this is a very small, my office. If you measure a speaker here, it's a real mess. It's a non-anechoic response. It's not good at low frequencies, but it's okay at high frequencies. It's doing okay there. So if we take the system, impulse response and look at this impulse response, here's a blow up of it. There's that reflection. If we remove it, then we'd have the high frequencies, and the low frequencies would not be correct. So how are we going to get rid of that flow reflection? Okay, this is the way we do it. We'll take, we'll notice that that reflection is a clean reflection. It comes from the acoustic center at low frequencies, not at high frequencies. At high frequencies, it's a mess, right? So, and there we have a measured impulse response, and there's the reflection from the floor. It seems much smaller than the other one, but the reason it's smaller is because the high frequencies don't come off in that direction for the speaker. There's actually quite a bit of low frequency there, though, which you don't see because it's very small on that curve. Here's the method that we use. If we look at that impulse response and look at the low frequency aspect of it, here's the direct sound, there's the reflection. If we take that impulse response, move it over by one delay time, and invert it, then this will be almost the same as that at low frequencies, okay? So if we take the impulse response, move it over by one delay, invert it, and add it, we've killed that reflection at low frequencies, not at high frequencies. And we can keep doing that 2 or 3 times. So we keep doing it, and in the end, you've got an impulse response that has no low frequency stuff in it until way back here. So now you're going to be able to measure it down to 30 hertz, 10 hertz, whatever, right? It'll be okay. And that's really the gist of what's happening. So here is an example of the impulse response that's so done. Now it looks like these things are, you didn't cancel anything, John. You didn't, but I did. There's no low frequencies in those. Those are the high frequencies, right? There's no low frequencies in those reflections. And when you do it, then you get the red curve is what happens when you look at just, if you truncate all the reflections from this point on, then you get the red curve, okay? There it is there. And if you look at the whole, if you look at this whole thing, it sort of looks like that. However, if we now look at the at this thing, what am I doing? Oh yeah, this thing here with all its reflection cancellation is that black curve. Okay, at high frequencies the black curve is nonsense because remember the high frequencies are not right. But it's okay below 500 hertz or so. So it's okay from here on down. So what we'll do is we'll take that high frequency end here and the low frequency end from there, and there's our response. And that should be a relatively good quasi-anechoic response. And you can see here what happens when I now take that frequency response and look at its impulse response, the reflections are gone, right? And here's the blow up of it. And if you might say, well, how do you know what the delay time is? Well, let's choose the geometric delay time, and let's muck it up and see whether we're okay. So what's going to happen is, I've shown 3 values there, 10% up, 10% down, and the nominal one is about right. And so that's the story. That's it. I'm finished. I'll answer questions, and then we'll try to get back to nursing my nose. Darn it.
Questions? Anybody? Just mostly concerned with.
Speak up, because I've got a little hard of hearing.
So when you have those copies of the response and you start copying them ahead so you can cancel
yes.
the reflection, how are you numerically deciding the coefficient that you're going to scale that to match the amplitude?
The scaling goes. If you look at the diagram I had, you know what the path is going to the reflection and back. So you just use the 1/R law. You have a direct signal that's 1 meter, and the other one maybe 2.5 meters. So it's down 2.5 times, right? And that's what you do. It's about 8 dB in this case. I didn't mention that, but that you need to know.
Okay. What's your as for truncating? You're doing a truncated part. What's your philosophy with the windows? Are you using rectangle or hand, small hand? What are you doing?
Say that again. What do you?
The windows are going to use to truncate the signal.
Oh,
just straight up.
I didn't use a window. I just used a rectangular. Yeah, I think I think one of the better ways to do it is to do a bit of a, well, a cosine window is better than a half hand. The half hand cuts too much of the low frequency off. And so you're better off to use a rectangular window. And in fact, when you do this to a speaker, and you notice the low frequency end coming to the high frequency end, pretty much agreeing with it, you feel good about it because you know that your crossfade or your stitching is going to be okay. That's pretty much what I think is the best way to say it. I'm sorry, I'm holding my nose. Clean the blood off there. What a party.
Oh boy.
There's blood on the dance floor. It's,
Hold on, I can see it.
this is the illuminator. Okay, there. This is forward. I don't know what that is.
Forward and back, I guess.
I don't know. It doesn't seem to be.
Doesn't it? All right, we'll figure
I
it
don't
out.
know, but maybe I didn't use it right.
It's my job to not use it right.
Okay, Gil.
Here somewhere. Bottom one, just keep going down. There we go. Nope, one more. There.
That one.
Still says John. Where's John? Justin. Let's try that again. Virtual acoustics. There we go. So when I want to get out of here, is it escape and then? Oh, there we go. And then
X out.
So I can do the player. Right. Hi, my name's Gil. If you want to know anything about me, go candonlabs.com. So I'm going to try to beat the clock here. I'm going to describe what I'm calling a virtual acoustics system, and this is from a project I did back in 2021. Okay, so what am I trying to do? In a nutshell, I'm trying to take a small physical space. The example that I was using was my kids' apartments here in Toronto, high-rise, very small apartments, and I'm trying to make them appear to be much larger acoustically. So that was the motivation originally for this, and then I kind of went down the rabbit hole. So in my personal opinion, most immersive audio experiences aren't truly immersive because the user can't actually interact with the acoustic space. So let me tell you what I mean about that. So consider somebody who's watching a movie or playing a video game. They got a surround system in their home, in their living room, and that video game or movie is taking place in a large cave, right? Well, as soon as the user talks, says something, well, they're not getting the sound of the large cave from the movie or the game. They're getting the sound of their living room, right? So that's what I mean. That illusion of being in the big cave is lost as soon as they make a sound, any kind of sound. So to create, in my view, to create a truly immersive experience that's realistic, all the sounds created by the user, so any kind of that's going on in the room, that has to appear to be in the same acoustic space as, you know, the large cave in this example, right? And by doing that, you allow the user to be part of the movie, part of the game, because you're right in there with them, right? So that's more the motivation. And as a furtherance of this, I'm not into the headphones thing, so you have to be able to walk anywhere in the room and still have that same big cave and have that immersion. So those were the goals for this. So it's a virtual acoustic system, VAS, and so I'll say VAS, I just mean this is the system. And so I developed it to try to create a truly immersive and realistic experience for people in their home. So this was being driven as a consumer-related product. So all the difficulties that come with being not having a team of engineers and weeks to set up and calibrate. No, somebody's got to take this thing out of a box, push a few buttons, and they've got the system. All of those difficulties were included in this project. I had to design some custom loudspeakers with multiple microphones and multiple drivers to be able to do this, and tons of DSP. And the first version of this,
that I'll be describing have 5 different presets, so 5 different acoustic spaces. So a forest, cave, a large gym like for basketball, a concert hall, and a smaller gym for like yoga or weightlifting. So what's the theoretical background here? So we have a room, that's the dotted line, those are the walls of the room. We have a green person here singing or playing violin or talking, doing whatever. The microphone picks up the sounds. The microphone signal goes to artificial reverb, spits out the speaker. They have the sound of the reverb from that cave, for example. And that's what the person hears. Easy peasy, it's all done. Thank you for coming to my talk. Not quite so simple. So, but in principle, that's what wants to happen. The person feels like they're in the large cave because this artificial reverb here is dialed up to be the sound of a large cave. And we can make this experience more realistic by adding some ambience and sound effects, so room tone. So if it's in a large cave, I might have dripping water sounds or some sort of airflow or something like that. And we might have some creepy background music just to freak the person out. Now for this to work, the biggest problem is going to be howling. So jumping ahead, howling is a big problem. And we have to use multiple approaches to try to suppress this howling. First line of defense is to use an acoustic echo canceller. So we're sending a signal. We know what we're sending out of the speaker. We pick up everything in the room through this microphone. And the path from this speaker to the microphone through the room has an impulse response. If we can know the impulse response for that, we can mimic it, cancel it out, and we should be able to break this feedback loop. We can and we can't. We can do a certain amount of it, but we can't do it perfectly. And so we have a secondary processing algorithms for doing howling suppression or anti-howling. I'll get into that. So from a user's perspective, what are the requirements? Well, we need a diffuse sound field that really fills the whole room and is truly immersive. And so we need to have sounds appearing to come from all locations. If I clap my hands, I need reverb coming from everywhere, above me, all around me. And the simulated acoustic space has to sound realistic. So our artificial reverberation has to be convincing, has to sound like those spaces. And for things to sound realistic, for you to actually feel like you're there, you need to have a pretty good low frequency response. Low frequencies are rather critical for feeling like this is real, right? It can sound nice without, but it doesn't sound real without the low frequencies. Again, this is intended as a consumer type of product, so we have to have a very minimal number of speakers. We're not lining the halls of somebody's living room with speakers, and basically the user can't be aware of speakers. They can't be listening to this cave and go, oh, the sound's all coming from that cave sound's all coming from over there. No, you have to, yes, I can see the speaker, but acoustically, I have no idea where the sound's coming from. It's coming from everywhere. As a consumer device, it has to be very easy to set up, and it has to be all self-calibrating. And as I said, the user has to be able to walk around the room and experience immersion and this experience everywhere they are. And I was going to add some ambient music and some sound effects to further enhance that experience. So what were my main technical challenges? Well, to do this, we need a very high gain from the microphone to the loudspeakers, extremely high gain, and therefore we have this very strong electroacoustic path. And we're going to howl. It's going to howl so bad you can't believe it. And it's going to be painful. And so you have to do something to deal with that. And we do a lot of processing to deal with that. We'll get into it. Just to make it a little harder, the acoustic conditions in that room are changing constantly. More people are coming into your living room, leaving your living room, you're moving around your living room, so that impulse response is changing constantly. Just by moving, I'm changing the impulse response. So I'm going to get more howling. And so those are things we need to take care of. We also need a good, as I said, a good sounding reverb, artificial reverb. It has to be multi-channel reverb. It has to actually have a quite high output channel count. And that algorithm needs to be able to simulate a wide variety of different acoustic spaces. We also want to create some randomness in the sound fields, some motion and randomness. We don't want things to be static, right? So if I'm creating a forest and I have birds chirping, I don't want the bird always there, right? It's like hit me over the head, there's the bird. Things need to move, things need to be random, or pseudo-randomized at least. latency is a big issue. And so, so we have latency due to the sound cards, we have latency due to the DSP algorithms, and latency limits how much echo cancellation you can do, because that echo's already come and gone by the time you're ready to figure out what it was. It also limits how small a room you can make. If I talk into a microphone and it takes 10 milliseconds for sound to come out of the speaker, that means the room already has to be at least 10 feet long, right? So if you have a 100 millisecond delay, you can only create rooms that are at least 100 feet long, kind of ballpark. You know what I mean? Latency means you can only simulate larger spaces, not smaller spaces. You definitely need a kill switch. As you're developing this, things are going to howl, things are going to go awry. You have to be able to hit a button and protect your system, your equipment. How do you test or tune the system? Because you're creating something that's, I'm going to talk in this room and it's going to sound like I'm in a cathedral or something. Well, I did a lot of singing. So 8 or 10 hours a day, I'm singing while I'm testing. Doesn't matter how it measures, it matters how it sounds, right? So never thought I'd get hoarse from developing algorithms. In this project, I was only allotted 3 to 4 months to do the whole thing, including hardware design and have prototypes built. And this was all at 2021, at the very beginning of 2021, height of COVID, height of lockdowns. I live on an island in the middle of nowhere, and equipment was very hard to get. You couldn't buy stuff, and you couldn't have it shipped. So it was really tricky. The first step was to design what I called a speaker cluster. And so it ended up being a, whoops. Let's skip these. So you have microphones, a bunch of DSP, and multiple drivers in this one cluster, this one enclosure. Basic idea, looking down overhead, we have 3 beams from the speakers shooting out. In fact, they're 120 degrees apart from each other, not quite as drawn. And also the ability to shoot upward. So if I have beams at 120 degrees and upward, I can also steer things all over, right? So that was the premise of how these things would be built. So I designed the clusters, and it took 2 months for the clusters to be manufactured and shipped to me. And so in the interim, I was using various prototypes, just using what I had available. I had 32 of these JBL speakers, and so I could do a bunch of testing and algorithm development while I was waiting for the actual speaker clusters to do the real work. I then migrated over to using Amazon Echo. The big advantage of the Echo was it has 3 drivers shooting in different directions in the horizontal plane and an upward driver. So that was useful for what I wanted, and a woofer. Compact, looks good for a demo, and they were available at Staples. So I could get a hold of some of these. I had to drain the shelves from multiple Staples, but I was able to get some of these in the middle of COVID. That's what it looked like after I connected directly to the drivers. I didn't use any of the electronics in it. So that was just for prototyping and getting started on algorithms. I also had to do a bunch of work on microphone arrays, so I was doing trying different configurations and writing beam steering algorithms, whatnot. So just in anticipation of getting the actual prototypes. So this is what it looks like. This is a cluster. It's about this tall, so cylindrical. So there's a mid-range and a tweeter shooting straight ahead, so that would be like shooting down, shooting straight ahead. There's the mid-range that's up-firing, and what you see here is duplicated on those 2 sides, so shooting out that way and shooting out that way. And then you have dual woofers that are force canceling so that the whole thing doesn't shake. So this is looking down from the top. That's the up-firing driver, and you can see the mounting for the microphones, for the microphone arrays. I was using Countryman Omnis because that's what I could get. Turned out I couldn't get enough of them, and so I drained what was available, and so I had to cut it down to 2 microphones per cluster. And so the beam steering was trying to always direct a null towards that upward firing speaker to try to limit the transfer from that driver to the microphone. So I was trying to reduce that path by having a null painted, pointed towards that driver. So in a practical VAS system, so here's a room, a typical living room. Looks actually just like my son's apartment, just a one-room thing. A little mini kitchen, couch, and a TV. The notion is you can't have just a single speaker and a single microphone. That's not going to give you immersion. You have to have multiple ones. You have to have multiple speakers and multiple microphones distributed. I found that you can get extremely good results with just 3. And as long as they're not collinear, as long as they're somewhat in a triangle, makes sense, you can get incredibly good results. So these clusters were, I had the 3 clusters in some kind of triangular shape. And the clusters are interconnected from an audio processing perspective. So the algorithms need to know what's going on in all the clusters, because we get echo paths from this cluster to this cluster, and so we have to do all kinds of echo cancellation, not just the microphones on a given cluster. So if you think about it, you have a cluster with four speakers, directions, and the microphones. You have to have separate echo cancelers from the microphone to each driver, but you have multiple clusters. So now I need an echo canceller from this cluster to over that cluster. So you have this whole large matrix of echo cancelers that need to take place. And independent signals are sent to each of the clusters, and different beams are sent to each of the clusters, including upward firing, which isn't showing here. And the idea there is we're going to take advantage of the natural reflections in the room off the walls, the floor, and the ceiling. And by having upward firing things, I can make a bird appear to come from up there because it's just bouncing off, like Atmos does, right? Like home Atmos. And this was, and like I said, 3 clusters works incredibly well, surprisingly well. So that's just the same picture, and I'm just trying to bring home the fact that you had 3 different processing units operating, all feeding into the room, and then their reflections interact. So the results of one cluster are feeding into the other just acoustically. So it's a huge feedback network, many, many different paths, lots of places for things to go wrong. So here's 3 different clusters again, blue, red, and green, and here are the microphones for those 3. What I wanted to point out was something that's pretty cool, recognized early on, is if somebody's walking up to one of the clusters, right, they see the speaker and they happen to get close to it while they're talking, if that microphone picks up the sound and spits it out of that cluster, oh, there's the speaker. Now I acoustically identify the location of the speaker. I've ruined my illusion. So I developed algorithms that were looking at all the microphones at all the time, could figure out when somebody was getting close to a cluster, and then what you would do is you would attenuate that blue microphone, turn it down in the blue cluster. So now, as I get really close to it, it effectively shuts itself down, but the other microphones, it plays back through the other clusters, and the microphones from the other clusters are picking me up, and they'll play back through that speaker, but because of all the delays and Haas effects, I never localized that speaker. So it was really pretty cool, and you could get really, really close to it, and you wouldn't tell that it was that. You'd often be wondering, is this thing even on? Right, which is beautiful, right? So that was a fun algorithm that was useful. I used Focusrite Scarlett because I could get them. And I connected 2 together via ADAT for this, and that gave me 16 channels in and 20 channels out. Everything's running. I wrote individual VSTs for each element of the processing, and we needed very low latency. Am I really tight? Yeah. So I'm just going to skip. We did anti-howling algorithms. Okay. So I had to do acoustic echo cancellation, as I described. From that, I got about 15 to 20 dB of echo or cancellation achieved per cluster. Then with the directional microphone, where I pointed the null towards the top speaker, I could get about 10 dB of additional isolation from the top speaker to the cluster. Within the reverb algorithms, I added pseudo-random phase modulations. And what that does is it gives it, if it's a fine line. You can't have, if you have too much, you hear the phase change as a pitch shift, but if you have a little bit of phase shift, then you stop resonances from building up at certain frequencies, and so you can cheat a little bit, and you don't get things that sound like they're about to ring, right? And then I developed a special dereverberation algorithm that removes all the tails of the reverb, which is important because things are bouncing around with long tails in the room, and I can crank up as much as I want, but I was using basically 15 dB of suppression. So with the 15 and the 10 and the 20, I had enough echo suppression, anti-howling stuff going on that the system was stable under all conditions. You could walk right up to the microphones, put your hands over it, and it would still be stable, which surprised me. You need to create different reverberant sound fields, and so I developed reverb algorithms. The ones I developed, I based it on the Lexicon 480, the old hardware box. I figured out the algorithms for that and then extended it, and I created versions that gave me 12 decorrelated output channels simultaneously to feed stuff. And I also developed a scalable algorithm for creating early reflections and echoes. Because sometimes you want an echo. Room tone, you want to create the sound of that cave or that forest. So I partnered up with a former student of mine who's works on films, sound designer, and we recorded ambient sounds and background noises. I live in a forest, so the forest preset was a no-brainer. That was really easy. It's my place. And I developed rotation algorithms to slowly move sounds around and shift the sound fields so that you'd get that random motion. That was quite nice. And then some background music, nothing with a melody. They're just notes here and there sparsely to set a mood. I'm not trying to have a song or anything, not trying to distract, just to set a mood. All right, so now I got to figure out how to get a playback. All right, so I'm going to play. I'm going to start off. This is Forest. This is just playing you the ambience and the music combined, just to give you a sense of what's coming out. It's a mono recording, not maybe it's stereo, but it's just the music and sound effects from the Forest preset. I'm just going to go halfway through this. So I have a stream that goes through my property. This is my place. You hear the piano music. We're just trying to set up, this one's just trying to set a vibe. I want to read a book. You know, I want to just sit there, casually, calm environment. That's the intent of this type of preset. So you get the idea for that. And next one I want to do is the cave. The cave is trying to be a little bit scary, a little ominous, a completely different, opposite mood from the forest. So when that suddenly appears behind you or somewhere or above you, it freaks you out. And it wouldn't be this loud, obviously, but you hear the dripping water. So you don't have the benefit of hearing all the reverb around you and all of this coming around you. That is really freaky at night.
And if I clap my hands in the room when that happens,
right, it's hard to show you this. I'm showing you this in pieces, right? It's hard because we don't have the setup. But that's like the sound effects, because what I'm about to show you is a video. You don't really hear the sound effects too much, but I wanted to show you the music and the mood behind these. So one was very calming and that, and this one was a little kind of freak you out thing. So to finish this off, where's my mouse? So I'm going to play you two videos. The first one, and so this is best as I can demonstrate it. This is me in living room kind of space. You'll see the three clusters in the room, and I'll have the system turned off. I'll talk, and then I'll turn the system on and talk and clap my hands and you'll get the idea, hopefully.
The virtual acoustic system is currently turned off,
Hold on,
so
hold
you
on.
can hear the natural sound of the room. Hello.
Is it behind me? No, I guess I have to. Just kill it. There I am.
The virtual acoustic system is currently turned off, so you can hear the natural sound of the room. Hello. The virtual acoustic system is now turned on to the forest preset. You can hear the reverberation on my voice, as well as different sounds in the forest, such as birds and the wind in the trees. Hello!
It's a Disney forest.
The system is now off, so you can once again hear the sound of the room. Hello!
So that's a Disney forest, and you have to bear in mind, you have three-dimensional reverb, right? You have reverb coming from all dimensions, picked up by an Omni mic on a phone, so you have one-dimensional output, right? So it sounds more reverberant than just the nature of things. But you can see there's a lot of reverb energy going on in there, right? And so, and the system,
feedback too.
yeah, to not be howling is quite a thing. And one last one I'm going to show you is a large gym. So
The virtual acoustic system is currently turned off, so you can hear the natural sound of the room. Hello! I have now turned on the virtual acoustic system to the large gym preset. You can hear the reverberation on my voice from the gymnasium, as well as the sound of balls bouncing and squeaking on shoes on floors. Hello! The virtual acoustic system is now turned off, so you can once again hear the natural sound of the room. Thank you. The virtual acoustic...
I think I'll just stop there. I'll tell you one last thing that was cool. I built 2 of these systems with the goal of having them in separate locations, 2 different cities, or my kids' 2 different apartments, or whatever, and having a phone link between them. And so, so you could be in the same space but remotely, right? And so I assumed that in some cases you would just have a phone link, a cell phone link, or some kind of thing. You wouldn't be able to have multiple channels or anything like that. And so I have all that working, and had it working. And a cool thing that I was so proud of was I got these clusters in the room, as you saw, right? And microphones on them, and I would track the location of the person talking. So now I know where my daughter is talking in her room, and I'm going to transmit just a mono signal, no directional information, but I watermarked into the audio that was being the communication channel. I watermarked in positional information, right? So that it figured out, just in real time, the microphones figured out where she was, and then when it played back in my son's room, there's a decoder that places her in the appropriate location to where she is. So if she's talking and she walks from there to there, my son hears her talking and walking from there to there. All over a mono channel. That was pretty cool. Anyway, that was the system.
So it seems to be a theme during lockdown. A lot of things happen.
Yeah.
I would take advantage of our garage to record acoustic guitar with spaced microphones.
Yeah.
This would solve that problem.
Yeah, I mean it's a lot of fun when you set it to like a big cathedral setting or something like that, and you just start singing. Or I had my son playing acoustic guitar or whatever, right? Yeah. It works remarkably well. And demo wise, when you're actually doing a demo, it demos itself. Because if you're going to demo this to like executives from some company and they're coming into the demo room, they're already, as they're walking in, they're already talking because they're important people, right? So they're walking in, and if they walk in and the system's already on and suddenly they hear their voices, your demo's over, right? They suddenly hear they're in this gymnasium or this cave. It sells itself. You don't have to explain anything. You just go, this is, you know, this is it. So, anyway, very fun project.
Yeah.
I think we probably have time for a couple more questions. Anybody else? So as long as people hold me.
For me, I just,
chairs.
you know, one of the things that you did testing the system, like singing a lot, I can see that, you know, an instant sort of commercial application of this technology is for, like, we're in a music faculty here. You have like, you know, like a choral ensemble that wants to rehearse.
Yeah.
It's kind of a soul killer to rehearse in a small room.
Yeah.
But not having to wear headphones or hold microphones, but be able to be singing in an environment that's a little more responsive, you know, in a small dead room, and suddenly it feels like something.
Yeah.
It's a lot, you know.
Plus, I've done it here. So in the studio here, you know, I have an array in the ceiling, and what I can tell you is that people who don't use headphones and you don't want them to use it, their tuning gets much better as soon as there's some form of reverberation and stuff like that. And that's what so it's kind of worth having it on mic if their tuning is better. You know what I mean?
Yeah. I mean, to that point, you know, I've been doing a lot of recording of artists and, you know, musicians. And you know, what do? You go to some fairly dry location or whatever, and then you add a bunch of reverb after. What I want to do, and I haven't tried it yet, is to just set up like some Neumann mics, and then they sing in this room and it creates it, and I would actually move the microphones around to find you know, a spot where the recording is good, but they're actually singing in that space, right? So I think they'll give a better performance. Right? The other thing I want to mention that was pretty cool is, you know, you turn the system on and you're in this cave and it's kind of whatever, and you're startled at first, right? And I tried this on a bunch of people that were naive, had no idea what I was doing, you know, here, just come listen to this, right? And people are freaked out at first, right? And then they get used to it, right? And then you're just sort of talking with them in this cave. And then when you shut it off, they're so freaked out by how small your living room sounds, right? They're just sort of, wow, what did you do, right? It's the learning curve and the adaptation curve for people was surprisingly quick, right? Like 20 seconds or something like that. And then they were just like, oh yeah, this is the space I'm in. Yeah.
What did all your neighbors say when you made all that noise in your apartment?
Oh, not me. I live on an island alone. I have my neighbors are a long way. I have deer and birds and stuff. And yeah, they're going, hey, there's Fred. I mean, they're in the soundtrack.
When you set up this system between, you know, your daughter and your son, the units, were they relatively exactly the same thing in terms of position?
No, not at all. They were, in fact, one system was based on the actual prototype speakers, and the other one was based on the what was the brand? Amazon, the Amazon Studios. So they weren't even the same speaker systems at all,
No,
and their positions weren't.
I mean the positions that they were or relative to themselves, because when you said that you recoded,
yeah,
your daughter was.
They were triangular in shape.
Yeah.
So and they kept this. They had the same ratios.
Yeah.
Oh, right. Like they weren't the same proximity, but they were similar. Similar triangles. I mean, to your point, if they were completely different speaker layouts, you'd have to get a lot smarter in your encoding. And I had 3 months to do this. Like I wrote every algorithm and designed the thing in 3 months. I was just pleased that it was largely proof of concept. The tracking.
I'm assuming position information is relative, basically.
Yes, it's where it would be to do it 100%. You'd say, well, my room A, these are my speaker locations, right? And you'd have to translate that over to room B at some point, so it would know your configuration, and then it could decode accordingly. But I wasn't really worried about that. It's all should be doable.
How did you transmit the positional information? Just it wasn't over the phone, presumably?
No, I watermarked it into the audio.
Oh wow!
I created a watermark.
That would go, and all you had was a phone connection.
I actually had better than that, but it would work under phone conditions anyway. But I was assuming in a worst case scenario, you would have just a phone connection for this to work, right? I was trying to have a worst case scenario.
Matrix did, basically.
Yeah, it's psychoacoustically hidden in there.
When you're listening to this, you're in a sweet spot, a triangular sweet spot, right? But when you go outside,
It still works. 100% works. It's glorious outside. In fact, I actually almost like it because I have the speakers going 128.
Yeah.
So I'm shooting stuff outside the ring of speakers as well, right? So if you go outside, you still get outside of the triangle of speakers. You still get the immersion, for sure.
Because it builds up in the space. That's it.
Well, it builds up in the
It
space,
needs
but
a certain amount of reflective energy in the space to work, right?
Yes, I mean you are. I mean for it to work outside of the triangle, you do need dry. You expect you're gonna have drywall and flooring and a drywall ceiling, right? But for sure, yeah, outside it'll bounce off the surfaces and track, and also ceiling stuff, because like this I haven't talked much about it. The ceiling reflections work remarkably well. So if you have bird flying over, it's just like wow, people are looking up, right? Like it works surprisingly well. Great, thank you.
Thank you,
Alan, for doing this.
How about a round of applause for all of our presenters?